So I was going through some Intro to QM by Griffiths problems, and I came across this one where he gave us the Gaussian distribution a times e to the negative lambda times x minus alpha squared, where a, lambda, and alpha are all constants. And he asked in part 1 to solve for a. That's why I thought, okay, well the objective is clear enough. So if you were to sum all the probabilities with respect to x from negative infinity to positive infinity, right? What should equal 1? Because that's the sum of all the probabilities, meaning something has to be happening. So all the sum of all the probabilities is 100%. Okay, I thought you just have to evaluate this integral so that equal to 1 and then solve for a. But as I was doing this, so as I substituted into here, I realized that by no amount of u substitution or integration by parts that I tried, you could not solve this integral using conventional methods. So as I delved a little bit deeper, I realized that this function is non-elementary, meaning if I were to take the integral of this function with respect to x, I need to use non-conventional methods to solve it. And so that's what we're going to be doing. But before I get into that, I'm going to first review a little bit of polar coordinates from Cartesian to polar, right? So if we imagine our typical xy Cartesian plane, and we have a point P here, and we say that this distance is length x and this distance is length y, and we attribute this length to r. Remember, this is a magnitude value. This is this is a magnitude value r, and we say this is the angle theta. But what if I want to write the values of r and theta in terms of x, and if I want to transform from x and y, from the x and y plane to these polar coordinates? So basically, I want to function in terms of r and theta, but I now have a function of x and y, and I want to basically go back and forth between these two. Well, first let's take out this triangle here. I'm going to put it over here. So we have the length r, x, and y, theta. Now you can use very traditional trig to solve x and y in terms of r and theta. So of course, r times the cosine of theta is equal to x, and r times the sine of theta is equal to y. So now we have this, meaning they're in terms of each other. But something that's, I think, more important for this specific problem is to realize that since this is in Cartesian coordinates, that the Pythagorean theorem still applies, such that x squared plus y squared is r squared. And I want you to keep this in mind and jump out of your seat once you realize it in this problem that's coming up. So I just wanted to show you that. Just a bit of a refresher for what's to come. Now, beforehand we had that probability function that I showed, but we're going to use something that's simpler and still attacks what we're trying to get at, which is this, e to the negative x squared. And if you were to integrate this, do the same thing that you did to the other one with respect to x, you of course come to the same problem of a non-elementary function. So I'm going to define this as being I sub x, or an integral with respect to x. And I'm going to define a second integral, I sub y, which is the exact same integral, but using y. And as a little bit of a picture of what's going on, if you draw just a simple plane, and here's y, I sub y, here's I sub. Now this isn't like what's on the side. Anyway, you'll see. Sorry, I sub x, I sub y, and here's the distribution. Y sub x would be this amount here, this area here, while I sub y is simply the same. Just imagine that's the same thing, but on the y side. So something you should notice is that these have exactly the same values. It's just one is plotted. It's basically a rotation from here to here, but the integral is the same value. So thus, I sub x is I sub y. And now we're going to use that information. We're going to multiply the two integrals together. E to the negative x squared dx e to the negative y squared dy. Now, both of these functions, or both are integrable on the same domain of negative infinity to positive infinity. So we can rewrite this as a double integral with the same domain. Sorry, I forgot the first one. Just imagine that's, okay, it's a little bit messy. Times e to the negative y squared, and then times dx times dy. Then I'm just going to take this piece over here, and I'm going to rewrite it. So we know that this is the same as e to the negative x squared minus y squared, which is the same thing as e to the negative x squared plus y squared. And so this piece right here, I remember I told you to look out for it. And I said that x squared plus y squared equals r squared. So then by using this, we can rewrite this here. But I want you to be careful about the domain here, because it's not the same. And I'll explain that in a second. So now we have this, and we need to think about what this is in terms of. Because at first glance, or if you're doing this really quickly, you might just use the same domain, and you may use the same variables. But we completely changed our system of coordinates, basically. We went from traditional Cartesian coordinates to now polar coordinates. And when you think about what's being considered. So, remember that the Cartesian coordinate, or the polar coordinates, are in terms of theta and r. So we need a dr. We need it to be with respect to this, and we need it to be with respect to theta as well, the angle. And something that happens strangely when you transform from Cartesian to polar coordinates, there's an additional factor here, r, known as the Jacobonian determinant. And I'll explain that in a little bit where it comes from, but it's not that important, just to know that it's there. Okay, so now we know what it's with respect to, but we need to now do the domain. So the purpose of this was to integrate between, or through, all values. So we need to think of this, and you can think of a circle. Right? And it starts at 0 radians, and a full revolution would be 2 pi revolution, or 2 pi radians. So the entirety of the values would be from 0 to 2 pi on this first integral here. And now think of this inner integral as being this piece, and the external as being the integral of the integral with respect to theta. So it's from 0 to 2 pi. And if we think of r, which is just this piece, we know that it's a magnitude, so it has to be 0 or greater. But it doesn't necessarily have an upper limit in terms of how long it can be. So it's from 0 to infinity. And that will give us all the possible values, which is exactly the same thing as this. Now for the Jacobian determinant, this piece here, it's basically just the determinant of a matrix found by Jacobian when you're going from polar to Cartesian and Cartesian to polar and vice versa. Yeah. But I mean, I could show you the matrix, but I don't think it's important. Just know that this is here. It stumped me a little bit at first, but yeah, I might show it later after this. Anyway, so we now have this, but something to think about is nothing in here is necessarily in terms of theta. So I can bring out this d theta, bring the d theta out here, because nothing's in terms of theta here. R isn't necessarily in terms of theta. The function is in terms of theta and r, but r is not in terms of theta. So, just going to write over here, it's running out of space. From 0 to 2 pi d theta, or d theta, 0 to infinity, e to the negative r squared, r dr. Okay, so now we have this piece here, which is simply 2 pi, right? So that is simply 2 pi. And then we're left with this, which, thankfully enough, we can solve. Thanks to this Jacobian determinant, we can now solve traditionally, which, I'm running out of space, but I'm going to say it's 2 pi. Now if you were to evaluate this here, becomes negative e to the negative r squared 2, evaluate at positive infinity to 0. Now you can check this yourself, but just take the derivative of this, negative 2 times r would come down, this would be 2r e to the negative r squared, and the 2's would cancel out, so it would just be e to the negative r squared times r. That's an activity for yourself to try, is this piece, I guess. And then we're left with the evaluation. I'm going to erase everything and just put this back. Okay. So remember, we were left with two pi negative e to the negative 2 e to the negative r squared over 2 evaluated from 0 to positive infinity. Now we can pull out negative 1/2. That's going to be a common factor between the two. So it simply equals e negative r squared positive infinity 0. Now you can evaluate this however you like, but if you think about it, if you evaluate e to the negative and then increase the r exponentially, well, this is going to be 1 over that value, e to the r squared. And as this increases indefinitely to infinity, this whole piece is going to become 0, because it's 1 over a very large number, which is 0. So it's negative pi times 0 minus, and then this piece here, evaluate 0, 0 squared, 0, e to the negative 0 is 1 over e to the 0, which e to the 0 is 1, so it's just 1, right? And so then this simplifies to negative pi. But is this our final answer to this problem? And now I want you to pause. Are these the same here? And think about what we did. Pause it. Think about what we actually did to come up with this. Oh, sorry, it's not negative, it's positive because of the two negatives. Are they equivalent? Well, what we did in the beginning was we actually multiplied I sub x times I sub y, which you can, since I sub y is equal to I sub x, it's the same thing as I sub x squared. So what we really found is I sub x squared. So we then take the square root of pi is equal to our integral with respect to x. Bada bam, bada boom. We have done it. But I posed the earlier question from the Griffiths textbook of solving for a. Now, in the question they gave, they provided this complicated integral that you could use, and so you put it in terms of that, like basically with the same form of that integral, and you use these factorials, and it was just kind of useless because there's something much simpler you could do. So we think our original question we can just use the fact, okay, so use the fact that, oh wow, that's dead. Just use what we learned, that we're going to call it z just for purposes. Square root of pi. Now we can just use that information later on. But first, let's make a substitution. First, let's make a substitution for x minus a. So we're going to let y equal x minus a. And you'll find that derivative of both sides, solve for dx. dy is just the same as dx. Also, we can bring out this a here. So this is the same as a. I forgot that bounds e is negative times y squared. Or, yeah, y squared. dy. Or this with respect to x is the, or this with respect to x, which is 1, so they're the same. Oh. Sorry, I don't know why I paused there. Anyway, so we make this first substitution, and we want to put it in a second, use a second substitution so that we can use the same form here. So if we were to take this, we can take the square root of each of these independent values to find it in this term, right? So if we say the square root of lambda times y, and we set it equal to z, we can now say that z squared, and these are going to be the same. So now we can let z, let z, sorry, I'm using a new marker, so it's a bonus. Let z equal the square root of lambda times y. So then we take dz dy, we get square root of y, or square root of lambda. And then solving for dy, we get dz over square root lambda dy. So using that, make the substitutions with here. A, negative infinity, positive infinity, e, negative lambda, or sorry, negative z squared now times, remember we had dz square root of lambda. And we can now take out this piece, square root of lambda. The same integral. I'm making this really big now so you can see it. E to the negative z squared dz. Remember, this is exactly what we had here, where this is equal to the square root of pi. Same thing as a square root of pi lambda. We know that piece is the same as 1. So then we solve for a, and a square root of lambda over pi.